Hello. Big apologies for not streaming yesterday. Uh, I've said a few times before, it's pretty busy right now. Um, I don't know if it's gonna get better or worse or what, but I'm trying to hopefully get better at streaming by doing it earlier in the day, because what I find is that my nights are usually pretty occupied. So I'm starting this one up. It won't be too long. Maybe, hopefully, we can reach an hour, and then I'll cut it. But yeah, so I'm gonna try and start streaming a little earlier when I do have free time, because I do have a lot of free time during the middle of the day. But sometimes at night, it seems like I get pretty busy, which is when I used to usually do these things. But time of the day doesn't really matter as long as I can get it done. And don't worry, I still made sure I solved problems, so we still have our streak. We're on a 20 streak right now, and maybe we'll get almost all of August, I guess. But also my contest that I did the other day came back, placed 3,000, which is my best placement ever, it seems. So yeah, that's pretty nice. Almost back at my peak rating of 1700, but 1698, I like it. Since I have a little bit of time, I say we get started on this one. So constructing a binary tree from pre-order and in-order traversal. So this one I don't think I can solve like on my own, because I do remember looking at the solution for this, and it was pretty tricky. Let me see. Yeah, I don't know if you guys can hear those sirens outside my house. As I said in a couple streams ago, I'm now at Georgia Tech in Atlanta, so I'm right in the city, so stuff's pretty loud. Let's see. Let's look at the solution. Morris. Oh yeah, all this Morris stuff. Depth first search optimal. What is this? O of n. This depth first search. O of n. Depth first search normal. O of n squared. Oh. Build tree, return root. Root equals whatever pre-order is. Mid equals in order dot index. Should we watch his video, you guys? I feel like he doesn't ever do a great job explaining. But we'll watch it
Hey
for
everyone,
17
welcome
minutes.
back, and let's write some more LeetCode today. So today I'll solve a pretty fun problem, construct a...
Here, I'll mute my mic so that it's not echoing.
binary tree from a pre-order and in-order traversal. So we're actually given two integer arrays representing 1, the pre-order traversal, and 2, the in-order traversal of a binary tree. And our goal is to take these two traversals and the orderings of those nodes and then reconstruct basically the original binary tree that the traversals are from. And it is technically possible. These two traversals have all the information we need. We just need to take that information and then deconstruct it and then reconstruct this binary tree from those. So just to verify it, let's go through this tree and actually do the pre-order traversal first of all. So first, we know pre-order traversal is you start at the root and then you process the current node, then you do the left subtree, then you do the right subtree, right? So let's just do the pre-order. So we're starting at the root. We do the root node first. That's how pre-order works. So then we get a 3. Next, we're going to go to the left subtree and then do pre-order traversal on that left subtree. We see 9, right? So we're going to add 9 to our pre-order traversal, and it doesn't have any children. So we're actually done with 9. We're done with 3. Now it's time to do the right subtree in pre-order traversal. So we start at 20, add 20 to our pre-order, go left, we see 15, add 15 to the pre-order. 15 doesn't have any children. Now we go to the right subtree, 7, so add 7, it's our last node. Higher left subtree, let's validate the in-order traversal of this tree. So we're starting at 1, we're starting at the root 3, but we're not going to add 3 yet. First, we're going to do the left subtree. We see we have a 9. The 9 does not have any left or right children, so now we can add that 9 to our in-order. Now, and construct this tree? Well, it's definitely possible. Let me show you how to do that right now. So I just want to let you know that there's actually two main facts that we're going to be using to construct this tree. So the first fact is that the first value in pre-order traversal is always going to be the root, right? We remember when we do pre-order traversal, right? We're always processing the root first. So if I was taking the pre-order traversal that we're given, right, we remember this is the pre-order traversal that we're given. The first value in pre-order traversal is always going to be the root. So this is the first value, 3. It's guaranteed to be the root because that's how pre-order traversal works. The first value in pre-order traversal is always the root node. Now we don't know about the rest of these, right? But we can recursively construct now the left subtree and the right subtree, right? We're done with this 3, right? Now our goal is to reconstruct the left subtree. Hey, lucky for us, the first value here is always going to be the root of the left subtree, right? Because that's how pre-order traversal works, right? So that's one thing that we're going to use. The first value is always going to be the root. And then we can take the sublist, right? We can remove the 3. We don't need to look at it anymore. Then we take the sublist, and then basically we're going to do this recursively. That's what I'm telling you. Okay, we can construct the root, but we need more information than that, right? And then let's say we're done looking at this 3 now. I want to take this array, right? And I want to know which values are going to go in the left subtree and which are going to go in the right subtree. From looking at the actual tree itself, we know the answer, right? We know that this is where we're going to cut our list, right? The 9 is going in the left subtree, right? These 3 values are going in the right subtree. But how can we determine that? Well, that's what we need our in-order traversal array for. Itself, we know the answer, right? We know that the right subtree. But how can we determine that? Well, that's what we need our in-order traversal array for. Okay, so now let's take a look at the input array we're given for the in-order traversal. And by the way, let me just mention that every value in the traversal is guaranteed to be unique. That's true for both of the traversals, the in-order and the pre-order. Every value is going to be unique because every value in the tree is going to be unique. But okay, so far we know that this first value 3 is going to be the root, right? So now let's find 3, right? We know 3 is the root, right? So we removed it from our first list basically, right? But now let's find it in our in order list. We find it's right over here. 3 is in this index, right? So we know we don't need this 3 anymore, right? We already created that node. But so now what does this in order array tell us? Notice how this is convenient for us. Every value to the left of the 3 that we just created the root from, every value over here, which is only 9, is going to go in the left subtree, and every value to the right of 3 is going to go in the right subtree. That's really convenient for us. Why is this the case? Because that's basically the purpose of in-order traversal, right? It guarantees that we're going to go through the tree in order, right? From left to right, basically. Right? So if we see the 3 here, and this is the position in the array, we know everything here is going to be in the left subtree, everything here is going to be in the right subtree. That's what it tells us. This is really convenient for us because we can count it, right? We can see there's exactly one value that's going to go in the left subtree, and there's exactly 3 values that are going to go in the right subtree. So what we can do is we can take the remainder of the pre-order array and then partition it, right? Partition it over here because we know one value is going to go in the left subtree and 3 values are going to go in the right subtree. So that's what we're doing, and we're going to continue this, right? So now let's and by the way, in the code, we're going to do this recursively. Let's create the left subtree. We know that, okay, this is the in-order portion, right? And this is how we're going to partition it from pre-order, right? We see this is the array to create the left subtree. The thing here is, notice how this is size 1, right? There's only one value here and there's only one value here, right? That tells us that the subtree we're creating is only going to have one node in it, right? So 9 is the only node in the left subtree. So we're going to create that node, put the value there, and now we're basically done with this left subtree, obviously, because there's no more there's no more nodes left in this general area, right? These values are reserved for the right subtree. This is reserved for the right subtree. Okay, so now we're looking at the pre-order portion, right? There's 3 values, just like in the in-order portion. And remember, how are we going to create the root node of this subtree now? We always take the first value in pre-order traversal. It's 20, right? The value is 20. So we're going to take this value 20. We don't need it anymore because we're going to create a node from that value. And so now we need to know which values are going to go in the left subtree and which are going to go in the right subtree. We know by finding 20, right? 20 is the value. Let's find 20 in our in-order traversal. It's over here. By the way, in the code, I'm going to be calling the index. We can get rid of it, right? We see that there's one value on the left of 20 and there's one value on the right of 20. This tells us that one value is going to go in the left subtree and one value is going to go in the right subtree, right? Just like we have over here. So now let's construct that left subtree. We know it's going to be exactly size 1 from looking over here. So we take this 15, right? Now our job is to recursively create the left subtree. We're going to take this 15 since it's the first value in the subarray for pre-order, right? We know that it's going to be the root of the current subtree we're at. So let's get rid of this 15. Let's create that node, right? 15 over here is going to be a node. And there's no more values left in this subtree because we know it's only going to be size 1. Okay, now we're creating the right subtree. We know that there's only one value in the right subtree from looking over here. And since there's only one value left in general, it's a 7. We can make a node from it. And then we're done. We know we're done because we've basically gotten rid of every single value in our arrays, pre-order and in order. So using these two arrays, we were able to create our tree correctly. And let me summarize what we're actually doing. We're not doing a lot. We don't need a ton of information. Remember, the first value in pre-order, the pre-order array is always going to be the root, right? That's just how it works. And then once we take that value, create a node from it, and then when we try to look that value up in order traversal, right? Then we can get some subarrays, right? We can take the length of the left and right subarray. So the right subarray is 3 and the left subarray is 1 node. Now these counts 1 and 3, they tell us how to partition the pre-order traversal. So take a look at the pre-order traversal. 1 tells us that we're going to cut over here because this needs to be size 1, this needs to be size 3. And then from this subarray with only 1 value, we are going to recursively run the algorithm to create this left subtree. And with this subarray, we're going to recursively run the algorithm to create this subtree. And we're just going to continuously repeat that process until we get to our base cases and until we're finished with every single node that we need to create. So now let me actually show you the code. It's actually very short, less than 10 lines. Okay, so as I mentioned, this is a recursive algorithm. So we always want to start with the base case, and the base case is going to be, what if we don't have any nodes to traverse through the two arrays that we're given? That means we can return null, or basically we don't have to create a tree. So if pre-order is empty or in order is empty, then we can return null. We have no values, so we don't need to create a tree. We can return null. Otherwise, we're going to create a tree node, right? And what's the value of that tree node going to be? Well, it's going to be the first value that happens to be in the pre-order array, just like I showed you, right? Always going to be the first value, so it's always going to be index of 0. And then whatever that value was, we want to find the position of it in the in order array. So in order dot index, so we want the index of that value, pre-order of 0, and we're going to get it in mid. Now this is the part where we're going to build the subtree. So root.left, let's create the left subtree. We want to find the position of it in the in order array. So in order dot index, so we want the index of that value, pre-order. Value, pre-order of 0, and we're going to get it in mid. Now this is the part where we're going to build the subtree. So root.left, let's create the left subtree, and we're going to do this recursively as I mentioned. So self.build tree, we're calling the function that we're inside of. And the convenient part about Python is we can do sublists, so that's going to cut down our code quite a bit. So we need to pass in the new pre-order and in-order arrays, or the subarrays more likely. So pre-order, what are we going to pass in for the left subtree of pre-order? Well, mid tells us how many nodes we want. The index of basically the value of mid tells us how many nodes we want in the left subtree. So what I'm going to do is for pre-order, we're going to start at index 1. We're basically skipping the 0 index because we already just created a node for the 0 index. We're starting at index 1, going all the way up until mid plus 1. In Python, this mid plus 1 is non-inclusive, so this subarray is really just a pre-order from index 1 to mid. So that's what we're doing. and we're going to pass in the in order portion that we need as well, and that's just going to be from the beginning up until mid, but not including mid, right? This probably makes more sense if you go back and look at the picture, but basically we're just creating the appropriate sublists that we need to create the left subtree. We're going to do basically the exact same thing with the right subtree. And I would encourage you to draw this out yourself to basically reinforce what you're learning or watching me do right now. So to build the right subtree, we need every value after this sublist, right? So we can just say starting at index mid plus 1 going until the end of the list. That's how you do it in Python. We're starting at mid plus 1 and going until the end of that sublist, just like I showed in the picture. And for in order, we can actually do the exact same thing. We want every node to the right of mid in order, right? From our in order array, we want every value to the right of this index mid. So we can do that with mid plus 1, starting at mid plus 1, and then going until the end of the array. So now let me close this function. And so this is literally all you have to do. The reason it's so easy is mainly because I'm using Python, but you could do this code without Python. It would probably just be a couple extra lines. You might need to pass in a couple extra parameters into this build tree function, basically just these indices that I'm doing. You might not be able to create sublists, but you can at least pass these indices into your functions in Java and other languages. So with that, we have actually created our tree. So the only thing left for us to do is return that tree. So with that being said, this is the final solution. It's probably less code than you would have predicted, but the problem is a little tricky, but it's kind of enjoyable, at least in my opinion.
All right, that makes sense. I won't implement it immediately because I just remembered that I have to do a SpaceX application, but one second, you guys. Let's see, where did I apply? SpaceX. Applied to summer 2027 software engineering internship co-op. Spring 2027, summer 2027 software engineering internship. Spring 2027. Alright, let me apply to this. 1 second, you guys. Attach my resume. School. Degree. Science. Alright, sorry you guys. Where is that space? Let me make sure I didn't miss anything. Microsoft, Databricks, Belvedere, HBS, Zipline, Notion, Apple Notion. Alright, let's software engineer. In a second, I have to do Databricks too. Provide a recent transcript. I think I have a transcript. One second, guys. Spring 28, fall, spring 28, fall 20, spring 28. EPAs. Let's choose the single you're most interested in. Okay, let's get back to it. So, if I remember, so if if not pre-order and not in order, return none. So let's see. Oh, so root equals pre-order at 0. And index is as IDX. That's not. Index equals in order dot index of root dot value, I believe. Then let's see. So 1, the index of 1 was 1, and then root dot left equals build tree self dot build tree pre-order in order. I don't know, that's not happening. So this is root dot right, and then we have to grab some pre-order of, let's think. Pre-order left here is 2 indexes, so index here is 1. Pre-order in order, pre-order here it's 2. So it's going to be 2, 0, IDX 2, then in order IDX 1 on, that would give 3 and 4, which is right. In order 2, 1. same thing. Doesn't seem right though. I mean, I guess it kind of is, right? Pre-order. For the left, it's everything. Like for example, if you're at 3, it's everything to the left of pre-order. So if you're at 1, it's everything. Pre-order is everything. Two, IDX plus 1. IDX plus 1 is, in this case, pre-order, it would be the IDX is in order, which is 0, 1, 1 plus 1 is 2. That's 1 and 2. It's just an IDX. But its answer is 2. IDX plus 1. 0, 1, 2. 2. And then it's from 0. You want to go from like 1 to IDX plus 1. And then in order, what would it be? For the left tree, you want to give it everything. You want to give it everything. I guess you want to give it every 1, you want to give it 2, not 3 or 4. So up to IDX. But not including it. Is this right? This doesn't seem right though. Index root value and object has no root, root equals pre-order at 0. Root equals is a tree node. Pre-order 0. Tree node has an object value. Too inefficient. Too inefficient. What is wrong with oops. Not pre-order. It's really the only issue. not preloaded. In order dot index is O of M. Index is canalist, which is NS. What? This doesn't work? Clearly I'm doing something wrong. Not pre-order or not in order. Root equals tree node pre-order in order root top val, which is the same as, it's the same thing, 1 to index plus 1 up to index mid plus 1 on in order mid plus 1 on return root. Really? Is this really, is root 3 over 0? O of n squared. What is the size of this? In order dot length. 2000. 2000 times 2000. That's into the 2, 3, 4, 5, 6. This is fine. Then I do another solution. But just copy his code. Submit that. It gets his own code is getting TLE. So if you, in the basic, we search for the roots of the linear search, frequently you have mathematics. Oh, I see. So basically, instead of doing it like that, you can do indexes equal, or ACs equals, because here we're searching up in order. Yeah. Alright, this is zero. That's right. Get the root value from pre-order, the current index, increment the index, look up the root's position and hash map, build a subtree. Okay. And then return none, otherwise root root equals tree node with a value of what is it? It's pre-order, right? Of pre-order Yeah, I don't understand. They'll let me play this? IDX. Root dot left equals DFS. index out of range, pre-index equals 0, pre-order, self-dot pre-index equals 0, 0, 0, 0, 1, pre-index equals 1, minus plus 1, oh, this is minus 1. Yeah, test case. Honestly, you guys, what are these people doing? What? Is this not what I submitted before? Tell me this isn't what I did before. If pre-order, if not pre-order, equals pre-node pre-order at 0. Index equals in-order dot index of the okay, and then left equals build tree pre-order of, let's see, IDX 0, 1. So this would be pre-order for 1. Let's try pre-order of, we want to give it for root dot left, we should give it just 2. So plus, so 1, 2, IDX, which is going to be this one. We'll do in order. We want to give it just 2 again. So just do up to IDX. And then here pre-order. Pre-order is for the right. It'll be 3 and 4. So 1 on, so 1 on, so 1 plus 1 on, so IDX plus 1 on. And in order would be 3 and 4. So this is plus 1 on. This is IDX. Same thing. IDX plus 1 on. Turn root. So this also works, but if I submit it TLEs. What? So, wait, where were the... How do I get back? Oh, here. Okay, so they just do a different thing here. Root equals tree node preorder 0. IDX equals in order dot index of here. Root dot left equals self dot build tree pre-order 1 2 IDX plus 1 in order 0 2 IDX. Root dot right equals self build tree pre-order IDX plus 1 on in order IDX plus 1 on. Return root. But if I copy this exact code, it doesn't work. What? Why is this the case? LeetCode when I submit my answer. Click on to see LeetCode for people who will be people commenting on this? Oh, so it works on LeetCode. Here, let's do it on LeetCode. What is this? Construct binary tree from pre-order and in order traversal. Pre and in, right? Pre and in, yeah. Okay, so if so for the right, it's going to be 20, 15, and 7. So index of 3, and the second one is 1. So 20, so x3 is 1 plus 1, so idx plus 1. And I think it's same for this, idx plus 1. Yeah, idx plus 1. Then over here, pre-order for the left, it's going to be 3, so 3 is 1. 1 is pre-order it's at 1, so we want just 9, so we want just 1, so we want idx to idx plus 1. Do we want 1 to idx plus 1? And for here 20, if it's 20, then 0, 1, 2, 3, 3, 0, 1, 2, 3. It's not 3 to 3, 0, 1, 2. It's just 1, 2, idx plus 1. 1 to idx plus 1 for 3 would be 1. 2, so 1, 2, idx plus 1, yeah. In order would be just 1 to 9, so it's up until idx. Does this work? Oh, look at that. Look at that. Build tree helper. Build tree DP. Interesting. Alright, you guys. So that puts us at a little over an hour right now. And like I said, I have something to do tonight, but we will definitely revisit this because that's pretty hard. I don't know if I mark this as a red or... Yeah, I'll mark it as a red because that was honestly not great. 8/22. Alright, yeah, we'll have to redo this one. But once I redo that one, now we're on just hearts. So that should be interesting, but I will see you guys soon.